Hello students, welcome to my lecture series on modern physics. So we are discussing solid state physics, different crystallographic methods to deal or to get the information about the crystal structure. In the last class we have seen the Bragg's law, so fundamental law to study the crystal structures. Okay, experimentally we can determine the crystal structure that we can compare with the theoretical predictions. Okay, fine. And that crystallography, in the last class we have seen the Bragg spectrometer. So on that Bragg spectrometer, one crystal will be placed on the rotating circular turntable. So another circular turntable will be there with the same axis, that is known as the ionization chamber is attached. So by measuring the ionization current versus the angle, we can see that for different angles, say for example first order diffraction is maximum occur at an angle theta 1, say at that current will be maximum. That graph also we have seen. So in this class first we will see the law equations, that is like a more general form of the Bragg's law, The equations we will deal. Then we'll see the crystallography by Love method, and we'll see the powder method. So fine. First we will see the Love equations. The topic will be crystallography by Love method. Crystallography by Love method. Okay, fine. So let us say for example I have the situation will be like this. I am taking a crystal plane. So this is a one crystal point, another crystal point. So lattice points, arrangement of atoms like this, and then we will connect with this. This is the lattice plane. Let us take this will be the lattice constant A, one-dimensional array I am taking. So we can generalize 3 dimensions also. Let us first take the one-dimensional array. Okay, fine. Let's say, for example, the rays so a ray of light is coming in this direction and falling here. Let us say I'll take with some color. A ray of light is incident from here. This is the ray of light which is incident. Let's say it incident at an angle some theta naught, glancing angle. Okay, then another ray which is parallel to it is coming and incident here. Obviously that is also the same angle, that is also same glancing angle theta naught. This we call as the incident X-rays. These are the incident X-rays. These are the incident X-rays. We have the scattered X-rays. So let's say there is a scattered ray from here, and let's say this is the scattered ray from here. Again these are parallel. So let's say this scattered rays makes an angle theta with the plane, and this also makes with the same angle theta with the plane. So these are the scattered X-rays. So scattered X-rays will interfere with each other, that may satisfy the Bragg's condition like that. So now I'll draw a perpendicular from here to here. We need to determine the path difference. So this is the perpendicular distance I have drawn. Let's say from the point A I have drawn the perpendicular, that is let us known as this perpendicular will be N. Now let's say this is the point B. Now from point B again you draw the perpendicular. This is the perpendicular, call it as M. Okay, now I need to calculate the path difference between these rays. So I can call it the first ray will be this. This is the first ray, incident ray. Then this is the first scattered ray, and this is the second incident ray, and this is the second scattered ray. We need to estimate the path difference. That is very important. So path difference we need to estimate. What the path difference will be here? The path difference between the two interfering rays will be A to M minus B to M, B to N. This is the extra path distance. This is the extra path difference, and here this is the extra. Okay, the net path difference will be AM minus BN. Okay, this optical path difference we need to calculate. So obviously I know this length, but this length will be A. So this is the length A. Apply for cos theta. Apply for cos theta. Then what I'll get if I apply for cos theta? Apply for cos theta. Then I'll get delta P will be is equal to AM is A cos theta. BN will be is equal to A cos theta naught. So clearly the path difference delta P is equal to, if I take A common, or otherwise do one thing. So let us define one vector along the incident ray direction. So along the incident ray direction I am defining one vector. Let's say along the incident ray direction I am defining a vector S. Say for example S naught is one vector along the incident ray direction. Along the scattered ray direction another vector I am defining, let us call it as the S. Okay, so if I take this is the A vector, this is the A vector, along the incident ray direction I have A vector and this is the theta naught. Okay, so angle between the A and this is the S naught. Similarly for this is the A vector, then along the scattered direction, this is the scattered direction, then this angle will be the theta. So if that is the case, I can write this will be like this. So A cos theta, that is the dot product with A and S vector, minus A cos theta naught, that is the dot product with A dot S naught. We can write like this. Okay, so I can write like this also, A cos theta minus cos theta naught. So if I take the A common here, A dot S minus S naught. Okay, so now this will satisfy the Bragg's condition. So Bragg's condition will be path difference will be is equal to n lambda. For constructive interference, the condition for constructive interference. Condition for constructive interference. The condition for constructive interference is delta P is equal to n lambda. So I'll substitute here, that is A cos theta minus cos theta naught will be is equal to n lambda, or otherwise A dot product with S minus S naught will be is equal to n lambda. So this is the equation we call as the Love equation for one-dimensional crystal structure. So Love equations. Love equations for one-dimensional crystal structure. Generally here cos theta we call as the cosine angle. So directional cosines. So we call as cos theta is known as the, I'll put some alpha, and cos theta naught will be is equal to alpha naught. We call them as the directional cosines of the incident and the scattered rays or diffracted rays. Directional cosines of the incident and scattered rays. These are the directional cosines of incident and scattered rays. Okay, fine. Even I can represent the same equations for three-dimensional arrangement also. In case of a 3D, three-dimensional structure, 3 dimensions. So for 3 dimensions, how we will represent this? So we have along x-axis and y-axis the base vectors. Along x-axis, let's say A, and this will be the B, and this will be the C. So that equations will become, so A dot S minus S naught will be is equal to, let's say along x direction I can put some nx into lambda. So along y direction B dot S minus S naught will be is equal to ny lambda. So along z direction C dot S minus S naught will be is equal to nz lambda. Okay, so here nx and ny, nz are the as usual integers. So nx, ny and nz are the integers. They'll have the values from 1, 2, 3 and so on. Okay, fine. So as usual here also there are the direction cosines. So along the x direction, if I take the direction cosine is alpha, then along y direction if I take beta, then along z direction along gamma. This we can write in terms of direction cosines. We can write in terms of direction cosines. In terms of direction cosines, we can represent this will be A cos theta. Cos theta is alpha minus alpha naught into nx lambda. So B cos angle will be, that is beta minus beta naught into some ny lambda. C gamma minus gamma naught into nz lambda. So this is the representation in terms of the lambda. Okay. So we have the one important relation I'll write here. What is that important relation is? So one of the important relation will be, that is very well known to you. So the direction cosines are interlinked with each other as alpha, beta, gamma are the direction cosines. I can write for the direction cosines as alpha square plus beta square plus gamma square will be is equal to 1. Alpha naught square plus beta naught square plus gamma naught square is equal to 1. So this is easy to prove also. Okay, fine. So these are the fundamental equations. Even from this equation we can derive the Bragg's equation also. Bragg's equation can be derived. So they are not different from the Bragg's equation. They are like way of representing another way, that's it. Okay, fine. Let's see what is that Lewis method, Low's method. I'm sorry, it is a Low. The pronunciation of L-A-U-E is the Low, but it is a name of a scientist. So name can be in any manner you can pronounce. Okay. So now let's see what is that Low method. So in the Low method, so I'll draw the diagram, or otherwise I have already the diagrams, I can copy and paste here. What is that method? Method I will take. So Low method, the diagram as follows. Let's see the diagram. So in this love method, the X-rays which are coming from the X-ray tube, so X-rays will be first passed through the slits known as the lead diaphragms. So, and there is a crystal and there is a photographic plate. So this is the crystal. This is the crystal. This is the photographic plate. So there is an X-ray which is coming and falling here. These are the X-rays which are coming. This is the crystal. This is the photographic plate. So photographic plate. So now X-rays are coming and incident there. These are the X-rays. So before passing through, they'll pass through the slits known as lead diaphragms. This is the X-rays are passing through the slits. There is a name, it is lead diaphragms. Now after passing through the crystal, as we discussed, it will scatter the X-rays in all the directions. The light will be scattered in all the directions. Light will be scattered in all the directions. So light will be scattered in all the directions. If you see the photographic plate will looks like this, the cone form. The photographic plate will look like the cone form. Okay, this is the central spot. Then there is a spots which are the bright constructive interference of the rays which are angle some theta. First order అనుకోవచ్చు మనం. Let's say this is the second order అనుకోవచ్చు. We'll see the circular pattern. Okay, this is actually cone shaped will come. There is actually the cone shaped will come. Only you are seeing this circular part. ఈ circular part మాత్రమే మనం చూడగలుగుతున్నాం ఇక్కడ. Okay, so X-rays from the X-ray tube after passing through the slits fall on the crystal. These are the monochromatic and they will fall here. They will scatter in all the directions. They reinforce in such a way that there may be a bright spots. So the bright spots will be, we can see on the photographic plate. They will look like in the form of a circular fringes. This is known as a Louis pattern. It is love pattern. Okay, fine. So I'll show you diagrams also how it looks like. It will be the cone shape. The cone shape looks like, it looks like in the form of a cone. Yeah, so this is the one. Incident beam. One more diagram is there. I'll take the diagram for even better understanding. Yeah, if you see clearly here, Just a second. Yeah, just a second. Yeah. Now you take this. So when you observe clearly here, the X-rays are coming from here. We can incident beam. Yeah. See here, this is the incident beam. So after passing through the collimator, so like slits type falls on the cluster. సో క్రిస్టల్ మీద ఇలా పడుతుంది. సో క్రిస్టల్ మీద ఇలా పడిన తర్వాత మనకు అందరికి తెలుసు, లెట్స్ సే దిస్ ఇస్ ద like plane, the light ray will be incident from here, that is X-ray will be incident at a glancing angle theta, and there is the reflection will be the same angle will occur theta. So now the deviation we can measure, this entire angle will be the 2 theta. So this is the incident ray and this is the scattered ray. The angle between the incident ray and scattered ray, that angle of deviation we call as the 2 theta. So now here is the crystal is placed. Some part of the light will be scattered in the forward direction, some part will be reflected back. So we can take the photograph of both, that is scattered in the transmitted light as well as reflected light. We have the both the patterns. The transmitted light, the pattern will look like in the form of the cones. So that can be seen here on the photographic plate very clearly. See, this is the thing. So this is the spots indicates of the bright. So that will be formed at an angle of 2 theta. So the cone angle will be, this is the cones will be formed here. Okay. So we have the diffraction pattern in the transmitted light also, and we have the diffraction pattern in the reflected light also. So even in the reflected light also, let's say that I have a diagram that can be understood better. The pattern will look like this. Just a second. Yeah, some problem is coming to copy it. Let us, I am copying again. Yeah, maybe this is not coming. There is some problem in it. Just a second. Yeah, this is the scenario when the light is reflected back. So when the light is reflected back, we will not see the complete cone. A part of the cone will be seen here. So this is a part of the cone that is seen. This is the back reflection. Okay. Fine. Yeah, you can see clearly how that back reflection situation will be. So you will not see the complete cone. A part of the cone will be seen in the back reflection also. Okay, fine. So this is the crystallography by Love method. So in this it is very simple. So based on the Love equations. So from X-rays will be coming from the X-ray tube. After passing through the X-ray through the slits, they fall on the crystal. The crystal will scatter light X-rays in all the directions. So we'll get a cone shaped pattern that is known as the love pattern. So on that cone, that is the circular part, we can see the dots. This indicates the diffraction or scattered light in reinforced to get the diffraction maximum. Okay, so there is a interference of scattered, that is transmitted light, even back reflected light also, both will be observed. Okay, fine. Now we'll go to the powder method. Crystallography by powder method. Crystallography by powder method. Okay, fine. So the difference between the previous method and this method, in the previous method we have taken the crystal, but in this method we will take a powder instead of the crystal. We will take a powder here. So okay. So what is the use of this method? So this method, again, just like I said, it will get the information about the crystals. So this method gives us the information about the size of the crystals, presence of impurities, distortion, preferred orientation of the crystals, all can be calculated. So this method will give the information regarding the size of crystals. Size of crystals, presence of impurities, distortion, preferred orientation, okay. So again, here also remember we use a monochromatic light. So monochromatic light we use in this experiment. We use a monochromatic light. How the diagram will looks like, that I will show you. So the diagram I will show you the first to for better understanding. So I have the image, I will copy directly and I will paste here. So remember the crystal in place of in the previous love method we have taken the crystal. Here instead of the crystal we will take the powder. Okay. So that how the situation will look like, I will explain to you. First I will take the photograph of it. Yes. Yeah. So let us take another photograph also. Better understanding. Yeah. So okay, fine. So in this powder method, a sample is taken in the form of a powder. This is the sample here. This is placed at the center of a film that will be in the form of a cylinder. This is the film in the form of a cylinder. The film in the form of a cylinder. So okay, the diameter of cylinder is provided. Diameter of cylinder, let us take the D. Now point where the incident beam enters, there is a circular small hole will be there. Through that X-rays will enter. So they fall on the, so they are entering here, they enter here, enter, and they fall on the sample. Once they fall on the sample, crystals here, the powder form, they will be oriented in random directions. So definitely there will be some crystal which satisfy the Bragg's condition, that is 2d sin theta will be is equal to n lambda. So once that will be satisfied, I will get a, so diffraction maxima, scattered light intensity will be maxima. So as I said, explained in the previous problem, according to the love equations, we'll get the patterns in the form of a cones. So the cone is clearly visible here, you see here, the cones will be clearly visible. X-rays are coming here, they fall on the sample, so it will be scattered at an angle theta. The angle 2 theta is the angle of deviation, that is angle between the incident X-ray and the scattered X-ray. Okay, fine. So when I photographic plated, so let me see, so when I took the photographic of these spots, so this is the part we can see on the film in the form of a sign. This is the spot, and this is the another one here. A part of it only we will see. This is the parts. A part of it we will see. A part of it we will see. Okay, fine. So this is the film. So when it is like after taking the photograph of this film, it looks like this. So the pattern how it looks this. Okay, even here also there is a transmitted light interference is there and reflected light interference is there, both will be present. So let us measure the distance between these two lines. So I want to measure this distance between these two lines. We can measure the distance between the two lines. So this is the length I want to measure, this is the arc length, this is length I want to measure. We can measure the length very easily. So okay, fine. How to measure the length here? See, so what is the total circumference of cylindrical film will be is equal to 2 pi r. So diameter is d pi. This actually corresponds to 360 degrees. Now I want the length. We want the length L. This corresponds to angle 2 theta plus 2 theta, that is 4 theta. If you see clearly here, so this is the incident ray and this is the diffracted ray. So incident ray and this diffracted ray, the angle will be of 2 theta. So when I want the arc length, this is the arc length I am calculating, this length I am calculating, this length L, and this angle theta, complete theta will be 4 theta. Okay, so what we can say here, we can say the length L divided by pi d will be is equal to angles 4 theta divided by 360 degrees. Okay, so length ratio will be is equal to angular ratio. Okay, or otherwise you can use arc length S is equal to r theta. The same thing I have written here. So 4 1 ja, 4 9 ja. So then from here, so theta can be written as, so 90 degrees divided by pi into d multiplied by length L. So the length can be measured. So the length can be measured here easily. The diameter of the film, that actually at the time of making the arrangement of the setup, we can calculate the diameter. Pi value we know, 90 degrees is anyway. Length can be measured from the experiment. After knowing this theta, now you substitute this theta in Bragg's equation. Putting in Bragg's equation, substitute in Bragg's formula. Substitute in Bragg's equation. when I substitute in the Bragg's equation, 2d sin theta will be is equal to n lambda. So from here d is unknown for me. D is equal to n lambda divided by 2 sin of theta. So n lambda divided by 2 into sin of theta will be this entire thing, 90 degrees L upon pi into d. So as I know the order of this maxima, n is equal to 1, n is equal to 2, n is equal to 3. So d can be calculated. Once d can be calculated, from there, so d will be is equal to, for a cubic crystal, it is a divided by square root of h square plus k square plus l square. So for a given crystal, for a given lattice plane, maybe 1 0 0 or 1 1 0 or 1 1 1. So I can estimate the h comma k comma l values, direction, cosines we get, that is orientation of the planes I will get. Or otherwise I can calculate the lattice parameter a also. Okay, so this is the powder method will helps us to determine the crystal structure. So and be careful here the difference between the love method. So and here is in the love method we have considered only a crystal. So but here it is a granules in the form of powder. So this method is easy. We definitely will give the diffraction patterns, and also measurement of this L is also easy on the photographic plate. So we can measure this length L. So that is distance between the, like, so one cone is there, that length will be that cone length. So this will be measured easily. Okay, fine. So this is the actually what is the powder method. So this powder method and the love method basically almost same, both are. So one is of, in one we are using the single crystal, same monochromatic light, and here we are using, here it is a powder, so the crystal like the crystals will be in the form of a powder here. Okay, fine. So the love method, there is a transmitted light as well as reflected light. Even in powder method there is a reflected light as well as transmitted light. Okay, I hope it is clear. So all the love equations will play the important role. So they are again the generalized forms of the Bragg's law. So they are not something new here. Okay, fine. I hope it is to you understood very well. I'm sorry, there is a problem. Yeah, so I'll stop for this class. This is enough for us. So you practice the sums on this chapter from your textbook or any material. It helps a lot. Okay, thank you.